This is the last of our 4 lectures on the microwave background and the first million years. And to be honest, so far we've taken a bit of a tourist route through the subject, taking an imaginary trip back to those early times to see the sights and hear the sounds. Now, while that's a reasonable approach for a lecture course like this, you won't be surprised to hear that it isn't the path most cosmologists spend much time walking down. In the professional community, the microwave background has one outstanding quality. It contains a huge amount of information about the universe. And in recent years, Herculean effort has been put into accessing that information, to use the microwave background to actually measure many fundamental cosmic properties. It's this more pragmatic theme that I want to explore in this lecture. How the properties of the microwave background tell us about the properties of the universe. Now let me start by illustrating the main aim of microwave background studies. Here is a wine glass and a teacup. Let's make each vibrate. Let's make it sing in its own voice. Well, of course they sound different because they have different structures and because they have different compositions. Material is different. This is true for all objects. They each have their own unique sound and sound spectrum. Now, the same is true for the universe. If the universe was slightly different, let's say it had more atomic matter or more dark energy, then it would sound different. We would see a different pattern of patches on the microwave background, which would have a different sound spectrum. So the whole approach is to turn all this around and try and work backwards, using the observed sound spectrum to figure out the properties of the universe. For our wine glass and teacup, if you were expert on vibrating structures, you could listen to those sounds, or perhaps study their sound spectra, and figure out the structure and composition of each. So, can we use this kind of approach to figure out the properties of the universe? Well, as you'll see, the answer is a very definite yes. And the method lies at the heart of Big Bang acoustics. Now, this is where our tourist approach really falls short. In last lecture, when I showed you the sound spectrum and you heard the sound, you didn't immediately go, ah, yes, 4% atomic matter, 23% dark matter. So it doesn't work. I'm afraid a simple intuitive approach just isn't appropriate. In fact, there are 3 crucial steps to the professional approach, and here they are. You must first thoroughly understand the relevant physics, in particular, how sounds are generated and changed during expansion. You must then put all that physics into a computer simulation which reproduces as closely and accurately as possible the sound in the young universe. And finally, you must adjust your simulation so that its calculated sound spectrum matches as closely as possible the observed sound spectrum. When the match is perfect, then hopefully these model properties are also the properties of the real universe. So for the rest of this lecture, we're going to look at each of these 3 steps in more detail. So let's start with the first, somewhat daunting step of understanding the physics. But I'm going to recast it in a slightly novel way that bypasses all the details using a linguistic metaphor. So you want to think of all the photons that rain down on us from the distant universe. The information they bring gives us a detailed account of where they've come from, their birthplace. It's as if the universe is communicating with us through light. It's telling us about itself. Now, the microwave background is our current example. You can think of it as an ancient panoramic document onto which is written the story of the universe's youth. Those patterns of patches are like a wall of hieroglyphs, and our task is to read them in order to learn their story. So, what language is this document written in? I mean, certainly it's not any human language, but it is in fact written by nature in nature's own language. Now, you may not have thought that nature has a language, but it does. It's physics. So to understand what nature is telling us, one needs to speak physics. It's quite intriguing that our brains are in fact able to learn this alien language, though for most of us it's at least as difficult as learning ancient Greek or Latin. But fortunately, there are those who are experts, and they've been poring over all those hieroglyphs, trying to figure out what they mean. That's our story for this lecture, how these experts approach deciphering this primeval document written by nature back near the dawn of time. Now, it comes as a huge relief to discover that much of the physics of the young universe is surprisingly simple. In a sense, the young universe is sort of speaking in a youthful, simple way, and there are 4 reasons for this simplicity. First, the young universe is almost perfectly homogeneous. It's just a smooth gas. Second, the components of this gas are themselves relatively simple and well understood. Light, electrons, nuclei, dark matter. And furthermore, the light, electrons and nuclei are all tied tightly together into a single coherent photon-baryon foggy gas. So for much of the time, there are really just 2 components, this photon-baryon gas and the dark matter. Third, in addition to being tied together in a single fog, the light, electrons and nuclei are also in thermal equilibrium. And to a physicist, this is the simplest kind of situation one could have. It's the kind that undergraduate textbooks routinely deal with. Finally, the deviation from exact homogeneity, in other words, the lumpiness, is very slight. And the physics of how slight lumpiness grows during the expansion is relatively straightforward. Physicists say the situation is in the linear regime, which means it yields to a particularly simple mathematical treatment. Now, having said how simple the young universe is, it still took almost 30 years from the 1970s to the 1990s for theoretical cosmologists to construct a detailed treatment of the hot, expanding gas laced with slight fluctuations. And some of the key contributors were Andrei Sakharov, the famous dissident, Rashid Sunayev and Yakov Zeldovich in the former Soviet Union, and Jim Peebles, Joe Silk, George Efstathiou and Dick Bond in the US, UK and Canada, though, of course, many others were also involved. Now, turning now to the second step in the overall project, knowing the theory isn't enough. One needs to actually calculate the primordial sound and its appearance on the microwave background. These calculations demand highly sophisticated computer programs run on powerful workstations. And the development of these programs has been a huge task involving many people, taking over 15 years to complete. Again, some of the key contributors were Ed Bertschinger, Naoshi Sugiyama, Uros Seljak, Matthias Saldarriaga and Wayne Hu. Now, perhaps the most famous computer program goes by the name CMB Fast. And as its name suggests, it uses some very clever methods to reduce the calculation time from days to seconds. Now, running these programs has become so important to cosmology that NASA has sponsored a public web interface as part of its Lambda project, so that even you could simulate your very own young universe. I'm not kidding, it's really very easy. Although I don't have time to go over the details, you don't need to worry about them because the default values all work just fine. So let me take you through how one calculates a young universe. There are actually 3 stages to the program. First, you must specify the basic parameters of the universe you want to calculate. So on the web interface, this includes things like the Hubble constant, and the relative amounts of atomic matter and dark energy and so on. There's also an important parameter we'll discuss in the next lecture that specifies the initial seed lumpiness emerging from the Big Bang itself, the set of organ pipes, if you like. With these now specified, stage 2 is running the program. In the 10 or so seconds the program runs, an incredibly complex set of calculations is being done. The lumpiness within each component is calculated as a sound spectrum, and as it responds to the pressure and gravity of all the other components. This sound spectrum is then tracked forward in time from the Big Bang. The calculations track the true variations in pressure and density, what in the last lecture I called the pure sound spectrum, P of k. You may recall this has a relatively clean set of harmonics, shown here in red at the time near 400,000 years. But remember, we don't see these waves directly, we only see the patches on the microwave background. So the third stage in the calculation is to follow the waves through fog clearing and calculate how they appear as patches on the microwave background. Stated a little more technically, we need to go from P of k to C of L, which is the angular sound spectrum of the patches seen on the microwave background, shown here as the blue line. This is a crucial step and includes some very interesting processes that I think it's worth taking some time to explain. Let me set the stage with a simple metaphor. As we look out at the microwave background and sort of record its sound, it's not unlike sitting way at the back of a rather bad concert hall with poor acoustics. Now, the true sound is deep in the gas. That's the orchestra playing the symphony down on the stage. But from where we're sitting, the concert hall has carpet and drapes that deaden the high notes, a ceiling that muddies the low notes, and our neighbours constantly rustle candy wrappers. So the symphony we hear has all these other effects added in. In the same way, you can think of the sound we measure from the microwave background, C of L, as a distorted version of the true sound, P of k. Now, pushing our metaphor a little further, if you already know what the symphony should sound like, then the distortions actually allow you to figure out quite a bit about the nature of the concert hall. So we anticipate learning even more about the universe from the presence of these sort of distorting effects. Now, in reality, CMB Fast must deal with about 8 or 9 of these distorting effects, but I'm just going to mention two or three of the more important ones. So let's begin with one that is relatively straightforward. Remember how the sound waves are being formed. We have slightly overdense pockets of dark matter surrounded by underdense regions. So gravitationally, it's as if there's a valley surrounded by hills, and the gas feels a pull into the valley. The gas falls into and then bounces out of these dark matter valleys, creating higher pressure and temperature, which makes the gas glow brighter. Well, if you think about it, while the gas is moving, either falling in or bouncing out, the light it emits is Doppler shifted. Gas moving towards us looks a little bluer and brighter, while gas moving away looks a little redder and dimmer. So the motion of the gas makes its own patches on the microwave background. Now, if you think very carefully about this, you'll see that the patches of maximum motion have intermediate size between patches of maximum compression and patches of maximum rarefaction. And so the effect of adding patchiness on these intermediate scales fills in the gaps between the harmonic peaks. And that's why C of L has much less prominent harmonics than P of K. The second effect was one of the first to be discussed back in the mid-1960s by Rainer Sachs and Artie Wolf, and it's called, perhaps not surprisingly, the Sachs-Wolf effect. It's really very simple. Imagine a photon coming from the middle of a region of excess dark matter. As the photon leaves the region, it has to sort of climb uphill to get out of the valley, where uphill means against the pull of gravity. Climbing uphill drains some of the photon's energy, so it gets redder. This is called a gravitational redshift, and it means that overdense regions will appear slightly darker on the microwave background because their light has been redshifted and so dimmed a little bit. Something that's important about the Sachs-Wolf effect is that it happens for regions of all sizes, including huge regions like the ones shown here. Now remember that the acoustic oscillations only occur for regions up to but no bigger than the sound horizon. Basically, there hasn't been enough time for gas to fall into and bounce out of yet bigger regions. Now, on this plot of the sound spectrum, with an exponential x-axis, which makes it look a little different from the previous ones I've shown you, the boundary is very obvious, with all the acoustic and Doppler peaks to the right of the sound horizon, which is about 2 degrees across on the sky. In fact, that whole region to the left is called the Sachs-Wolf plateau. In our metaphor, it's the deep hum of the air conditioners and is unrelated to the sound of the symphony. Going back to our boundary between the small acoustic patches and the large Sachs-Wolf patches, you may not have realized that most of what your eye sees in those lovely microwave background images is in fact the Sachs-Wolf effect, not acoustic waves. Here's a diagram showing a whole range of patch sizes, first across a quarter of the entire sky, and then across a small 10 by 5 degree subregion, with the range of patch sizes between 2 degrees and 1/10 of a degree shown as little circles. Now here's where those patch sizes end up on our sound spectrum. You can see that even the largest acoustic waves, which are not much bigger than the full moon on the sky, are tiny when you place them on these grand all-sky maps. You can also see why it's so important to have high angular resolution. The WMAP image here is not really adequate to probe the higher harmonics, which is why the next satellite, called Planck, is designed to have much higher sensitivity and resolution. So let's now consider these smaller waves. They appear over on the far right of the sound spectrum, and you can see how they seem to have been suppressed. In our concert hall, this is the equivalent of carpets and drapes deadening the high pitches. For the microwave background, there are actually 2 effects responsible for this apparent suppression of small waves. Let's have a look at those now. The first effect arises because the wall of fog on which we see the sound waves is itself somewhat fuzzy. It has depth. Remember, the wall arises from us looking out into space back in time through the period of fog clearing. But since it took thousands of years for the fog to clear, then the boundary between fogginess and transparency is itself thousands of light years deep. So, if a sound wave is smaller than this thickness, then both the peak and the trough are within the wall's thickness, and they get blurred together. And so the wave appears washed out. We don't see it, and that suppresses the sound spectrum. Now, the second effect arises because, despite what I've told you before, the universe isn't completely transparent. There's a misty curtain lying just in front of the microwave background, which blurs the patchiness and suppresses the sound spectrum. Here's what's going on. As we learned in Lecture 13, 400,000 years after the Big Bang, the universe turned from foggy to transparent, as it turned from ionized gas to atomic gas. And at that point, the universe began a long period of ever colder darkness that's come to be called the Dark Age. Now, we'll visit the Dark Age in Lecture 18, but for now, just know that after about 400 million years, the first stars were born, and their powerful light began to re-ionize the neutral gas, reversing, in a sense, what had happened at 400,000 years. Now, this ionized gas introduces a thin mist, and so we actually see the microwave background through this mist. And as you might imagine, this blurs its appearance and tends to make the smallest patches less visible. So the high-frequency sound waves appear to be suppressed. Now, you might wonder why ionized gas at 400 million years is only a thin mist, while ionized gas at 400,000 years is a dense fog. And the answer is that by 400 million years, cosmic expansion has made the gas so much thinner that it's only a misty curtain rather than an impenetrable fog. Okay, look, that's enough of these complicating processes. Really, don't worry if you didn't quite follow them all. Just recognize that they are sufficiently well understood to be included in the final stage of the CMB-FAST calculations, which brings the simulated young universe right to the point that it can be compared with data. In other words, it calculates the sound spectrum C of L. Here, for example, is the calculated sound spectrum for the model I showed you earlier. Now, if you run your own models, this plot, along with other things, is what's returned to you when the program's finished its calculations. Now we come to the third and final part of our primary project, which is to use the sound spectrum to measure the properties of the universe. We try to find a set of input parameter values for CMB-FAST that result in a calculated sound spectrum that matches the observed sound spectrum. Now, at this time, I'm actually not going to focus on the actual derived parameters because we're going to use Lecture 26 to discuss a much broader program to match cosmological models to 4 or 5 quite different cosmological data sets, only one of which is the microwave background. But here, let's just concentrate on seeing to what extent CMB-FAST can actually match the observed sound spectrum. Now, someone who's worked quite hard on this kind of model fitting is Max Tegmark, and I'm going to be using some of his movies in a moment. So the simplest way to illustrate all this is to vary just one parameter at once and watch the change in sound spectrum. It's a bit like playing a set of violins, all identical except for the type of wood they're made from. Here's one of Max's movies showing how the calculated sound spectrum changes as we increase the total cosmic density. Clearly, as the total density increases, the entire sound spectrum shifts to lower frequencies. Denser universes have deeper voices. Look at how the data really single out a specific density as the true one. The real universe has a well-defined pitch, and this pitch tells us, within about 1% accuracy, what the total density is. Now, just for fun, let's listen to the primordial sound of 3 universes spanning a range of 40% in total density. The change in pitch is really obvious, and the middle one matches the observed data best. Now, that was the total density. What about the fractional density of different components? Here's how the universe's sound spectrum changes as you change the relative amounts of atomic and dark matter, from no atomic, that's all dark, to all atomic, that's no dark. You can see how the first peak gets much stronger, while the location and strength of the higher harmonics change more subtly. Again, the data clearly pick out an atomic content near 4% and dark matter content near 23%. As before, it's fun to see what these different universes sound like. Here's 3 models with atomic matter content set at 8, 4 and 2%. And I've plotted the fundamental peak at the same height so that you can see more clearly the difference in the higher harmonics. That's actually a nice example of how the sound spectrum easily picks out the difference, but it's actually quite difficult for our ears to hear the difference. Now, my last example is to vary the time at which the first stars form. Remember, they reionize the gas and create a foreground mist through which we see the microwave background. With no foreground mist, the model lies above the data. But as the mist gets thicker and thicker, the microwave background appears more and more blurred, and its patchiness gets washed out, so the measured sound spectrum gets weaker and weaker. The data suggests the mist isn't very thick, about 92% transparent, which corresponds to a time for the birth of the first stars around 400 million years, with an uncertainty of about 30%, which, if you think about it, is a really quite remarkable measurement. Well, let's bring this lecture to a close by returning to our graph showing the best microwave background data and the best model fit as of about 2007. The model has a total of about 8 parameters, many of which are determined to within a few % accuracy. As I mentioned before, we'll postpone to lecture 26 a fuller discussion of all of these parameters when we bring in all the other data sets. But for now, I want you to step back and let the full message of this diagram hit you. It's far too easy to get lost following the details and miss the stunning nature of this plot. First, the observations. Just look at the tiny size of those error bars, at least over the first 2 peaks. And when the results from the next major satellite are added, the European Planck Surveyor, they will be similarly small across the entire plot and beyond. This is a fabulously exact measurement of the acoustic structures present in the young universe, and there is no mistaking the wonderfully rich spectrum with its harmonics, low-frequency plateau, and high-frequency damping. But even more impressive, I think, is our ability to model it so accurately. This is not some broad, featureless spectrum that might be explained by all kinds of general mechanisms. No, it has multiple peaks of specific height and location, and our model gets them all correct, passing right through the data points. I think this plot, more than any other I know, should convince you that we're on the right track. That what I've been telling you about the first million years, with its foggy brilliance, its endless sea of dark matter, its deep, surging sound waves, is not just a modern myth. It all actually happened, long, long ago, before the sun and earth had formed, and well before you and I were here to wonder how it all began.